In exercises 3 through 20, sketch the curve represented by the parametric equations, indicate the orientation of the curve, and write the corresponding rectangular equation by eliminating the parameter. We have x equals t to the third, y equals t squared over 2. We've chosen negative 2 to 2 for the t values. So let's plug the t values in for the x. So we have negative 2 is negative 8. Negative 1 to the third is negative 1, 0, 0. 1 is 1, and 2 is 8. Then we have negative 2 squared is 4 divided by 2 is 2. We have 1 half, 0, 1 half, and then we have 2. I was thinking 4, but then 4 divided by 2 is 2. Negative 8, 2. Plot that point. Negative 1, 1 half, 0, 0. 1, 1 half, and then 8, 2, and we have to pay attention to the order that these are plotted in, because that'll be the orientation of the graph. That'll be the direction that we graph this in. So we make little arrows to indicate that this was graphed from left to right. Now we have to eliminate the parameter. So we have to get one of these to say t equals. So t is equal to the third root of x, and then we'll replace the third root of x. We'll replace the t with the third root of x in the other one. So we have y equals the third root of x squared over 2. And you can put the squared on the outside or the inside in this case. In the second example, we have the exact same instructions. We have x equals square root of t, y equals t squared minus 2. Now we've chosen perfect squares for t because of the square root. We have 0, 1, 2, and 3. And let's plug the t values in for the other one here, for y. We have negative 2, negative 1, 16 minus 2 is 14, and 81 minus 2 is 79. Now, the y's go up pretty quickly, so let's go by tens. We have 10, 20, 30, 40, we have 50 here, 60, 70, 80, and 90 here. 0 is negative 2, so maybe it's there. We have 1 is negative 1. 2 is 14, so 2 is up to about right there. And then we have 3 jumps all the way up to 79. So we have this shape right here. Now we're supposed to keep track of the direction that it's graphed in, so make the little arrows that it was graphed from left to right. Let's get the Cartesian equation. We need one of these to say t equals, and it can be either one, but it looks like x would be the easiest. So we square both sides, and we get t equals x squared. Now we're going to replace this t with x squared, and we get y equals x squared squared minus 2, which is equal to x to the fourth minus 2. In the next example, we have x equals 2 cosine t and y equals 4 sine t. Now we've chosen radian measurements, and we're going to go all the way around the circle. And we're choosing the easiest one we can choose, and then once you do a few of these, you'll know that this is an ellipse right away. The cosine of 0 is 1, so we have 2, 0. Then the cosine of pi over 2 is 0, and that makes this 4. Pi is going to be negative 2, 0. 3 pi over 2 is 0, negative 4, and 2 pi is back to where we began at 2, 0. So let's plot this. We have 2, 0, 0, 4, negative 2, 0, and 0, negative 4. And we'll draw the ellipse that this creates and try to keep track of the direction that we went. We went counterclockwise, and so we'll make the little arrows to indicate the direction that this was graphed. And that's probably good enough there. The Cartesian equation, we're going to use the Pythagorean identity. That's sine squared plus cosine squared equals 1. So x over 2 is equal to cosine of t. Y over 4 is equal to sine of t. And so x squared over 4 plus y squared over 16 is equal to 1. Example of when to do x equals instead of y equals. Now if we isolate t here, we're probably going to have some sort of plus or minus with the absolute value, and we'd rather not mess with that. So why don't we do this? Why don't we have y plus 4 is equal to 3t, and then t is equal to y over 3 plus 4/3. And then we can replace the t in the absolute value and have x equals the absolute value of y over 3 plus 4 over 3. And having x equals instead of y equals is perfectly acceptable. We would like it to say y equals, but it doesn't have to say that.